Okay, we will start now. So, good day to everyone and welcome to Maccaferri Philippines Geosynthetics Movement Live Webinar. My name is Janelle and I'll be the moderator for this session. Before we begin, I have a few items to mention. Please be reminded to mute your audio for the whole duration of the webinar. Please do not interrupt the speaker. If you have questions, you are welcome to type it on the chat box and we'll bring them up during the Q&A session. I will also be administering a few feedback questions for your input. Kindly check your inbox after this session. It is not mandatory, but it will be an opportunity to provide Maccaferri Philippines with any comments or suggestions regarding this webinar session. This session will be recorded. You will receive an email with the webinar recording as soon as we have it ready for you. Certificates will be available upon request. Kindly provide your complete name and email it to j.pagtakhan@maccaferri.com. Today, we are presenting the Geosynthetics in Ground Improvement. In this live webinar, you will learn more about the prefabricated vertical drains, the bearing capacity improvement using GeoGrid foundation raft, the basal reinforcement for embankments on subsoil, and the GeoGrid encased stone columns or GESC. Now, I'd like to take the opportunity to provide a brief introduction about Maccaferri. We are a global company with more than 70 subsidiaries operating in 5 continents. With an on-site presence in more than 100 countries and over 3,000 employees, we are highly specialized professionals trained in designing and developing complex solutions in the civil engineering, geotechnical, and environmental construction markets. Our presenter today is Clement Fajardo, the Technical Business Development Manager of Maccaferri Philippines. Clement has extensive experience in engineering, geology, geophysics, and geotechnical engineering. He graduated from Mapua Institute of Technology with 2 degrees, BS Geological Engineering and BS Geology, and has units in Bachelor of Science in Civil Engineering. He holds a master's degree in geotechnics engineering from Missouri University of Science and Technology. Being an active member of the Geological Society of the Philippines and the Australian National Commission on Large Dams, or ANCOLD, he has assessed and designed various mitigating and ground improvement measures for geohazards such as slope stability, ground shaking, and foundation problems involving dams, buildings, bridges, and other structures all over the Philippines and in Papua New Guinea. Now, without further ado, we will turn the time over to Clement Fajardo. Hello, Clement.
Hi, thank you
Hi.
so much for that, Janelle.
Thank you.
Can everyone hear me?
Yes.
Okay. Can all see my screen also?
Yes, Clem.
Okay, fantastic. All right, so let's start. So again, good afternoon, everyone. It is again my pleasure to welcome you all to Maccaferri's webinar. My name is Clement Fajardo, and today we'll be discussing one of the most interesting topics in geotechnical engineering, and that is geosynthetics in ground improvement. So an overview of the topics we'll be tackling today. Here you go. So I'm quite certain that many of our audiences today, you guys already have an idea of these here. So prefabricated vertical drains, bearing capacity improvement using GeoGrid foundation raft, basal reinforcement, and GESC. So what we're going to do today is to show you the advantages of using these new systems as alternatives to other ground improvement methods, such as, for example, some of the ground improvement methods we have here is piling, grouting, soil nailing, cement chemical mixing, and etc. So to start it off, let me first define geosynthetics. These are planar products manufactured from polymeric material used with soil, rock, earth, or other geotechnical related material as an integral part of a civil engineering project, structure, or system. So they are made up of polymers, steel and fiberglass, and other natural materials. In fact, In today's world, geosynthetics have already transformed geotechnical engineering to the point that it is no longer possible to do geotechnical engineering without geosynthetics. So that means because it has become very popular due to its wide range of application, we have now had many functions of these geosynthetics. These include like separation, it can be used for filtration, drainage, reinforcement, and barrier and erosion protection. So now, with that being said, let us move on to one of the oldest methods in geosynthetics, the prefabricated vertical drains. Another name for this, by the way, is wick drains. So this method is actually a quite old method. It was established in the 1980s, which originally replaced the sand drain method. So the primary function of these PVDs is to accelerate the primary consolidation. In other words, its use is to decrease the overall time required for the completion of primary consolidation due to preloading. So this is your surcharge load, and these are your prefabricated vertical drains. So what's going to happen is because these drains have higher permeability than the surrounding soil, water will seep towards the top and then be drained through this drainage here. Another objective or another function of this is it will decrease the amount of surcharge required to achieve the desired amount of pre-compression in a given time. And because of this, you will have an accelerated consolidation settlement. To further show that, so vertical drains such as this, they can also be used as pressure relief wells. So by adding these vertical drains here, we can reduce pore water pressures or excess pore water pressures below the natural slopes or below your surcharge load. In other words, you can also have a lower surcharge load or lower embankment because of these vertical drains. So this will entail project savings. You'd have higher project savings. So it all started with Terzaghis 1D theory of consolidation. So he said here that you would need to that the total consolidation settlement is time dependent. So the settlement occurs in a given time after construction, and the time taken for settlement will decrease. Okay, so there are two ways to get the properties for your settlement, right? So either you can get the settlement the parameters using SPT correlation data, or you can get it using the odometer test. The parameters we use in order to get the settlement would be mainly three. The coefficient of consolidation, coefficient of compressibility, and the compression index. So this is a product of Maccaferri, the prefabricated the vertical drain, the Mac Drain VD, and here are the technical specifications. So we have 4. So whichever you would use, that would depend on your on the requirements of the project. So this image summarizes the installation of PVDs. So first, you would have this is the original ground. You would then add a sand blanket over it, and then position a anchor plate. So of course, you do this using your mandrel, and then folding the PVDs. So folding this is required so that when this PVD enters the soil, it's not going to get damaged. Doing this will also prevent the overlying soil from entering to the hole or it will prevent other sediments from entering into this layer here, the PVD. So once we do that, you're going to install that here by pushing the PVD, and then until you reach your target depth. Once you reach your target depth, you will withdraw the mandrel and then cut the PVD and Voila, there you go. So this is a project we did where Sumimoto was the project owner. The general contractor was Bauer Foundations Philippines. Consultant here was Sumimoto, and we supplied 100,000 linear meters of Mac drain. Here. So this is Taganito Mines. Is located in Surigao del Norte. So what happened here was because of the thick deposits of clay soils and the presence of shallow groundwater, the best way to mitigate this was by using PBDs. And this is a picture of the ongoing construction of the PBDs, our installation, and this is the near completion, and the final product will be here. So by the way, there are two. You can use either square pattern or triangular pattern in installing these PVDs. Here, I think we use square. All right, next. So now we're going to move on to the GeoGrid Foundation Raft. So bearing capacity improvement using GeoGrid Foundation Raft. So as we all know, one of the most common uses of geogrids is in road construction. So geogrids can serve as a construction aid over soft subgrades. It can also improve or extend the pavement's projected service life and reduce the cross-section for a given service life. So this is without the geogrid, this is with the geogrid. So for this project, this is one of the common ways to use the geogrid, right? This is for subgrade improvement. So what we did was we installed 3D cellular confinement system and MacTex non-woven geotextile. Now this is for Philippine airport to improve the subgrade under the road or under the airway. Next, another common use for the geogrids is for MSE walls. So this project was with Steel Asia, which included retaining wall reinforcement, steep reinforced slopes, and reinforcement in a variety of landfill applications. So here we supplied the MSE wall here, as you can see here. So this technology is most suitable, can also be used for shallow foundation or to improve the subgrade material underneath the footing. So you would be able to do two things with this system. You would increase the bearing capacity and you would reduce the settlement. So, and on this left figure here, you can see that on the left side, we have two scenarios where the subsurface material is unreinforced and we have here the reinforced one. So in order to determine the effect of these geogrids with respect to the applied pressure and settlement, we can look at this figure right here. So what they did was they conducted plate load testing on both unreinforced and reinforced foundations. And we can see that the geogrids, which is this line here, by installing geogrids, you have a higher applied pressure with respect to your settlement compared to the unreinforced subsurface material. Now, the bearing capacity of unreinforced road on soft clay subgrade is shown here, right? So these are formulas for roads. Though it's not for the foundation, we can see that the bearing capacities increase by twofold right here. And if you do not have the undrained cohesion, there's an empirical formula which you can use. If you have the CBR or the California bearing ratio, you'll just multiply that by 30. Okay, so this is the design mechanism applied when you're designing a geogrid foundation or geogrid raft below the foundation. So the load, as you can see here, this is the load. It spreads through the layers according to their spreading angle. So there's a particular spreading angle right here. So the reinforcement function has been shown to fall between two main mechanisms. You have the tension membrane which is, and the lateral base course restraint, which is your engineered fill. So in the first layer, at the interface with the subgrade, it is subjected to the highest amount of vertical deformations. So when the first soil layer is spread and compacted due to the settlement of the subgrade, the next geo layers instead are far less subjected to displacements because of this load distribution we have here. So similarly with roads, right? This can also be applied to your shallow foundation. So as you can see here, the effect of using GeoGrid on road improvement, which can also be applied to raft foundation, you can either, in the roads, you can either increase the number of passes while maintaining the respective depths or thicknesses of the layers, or if you want to save a lot in your project, you can reduce this and still have the same performance, as you can see here. Now, when we have weak soils, we must opt to use different ground improvement methods to increase bearing capacity, right? So as we are already aware, we consider the for bearing capacity, we consider two, right? That's shear failure and settlement failure. For the shear criteria, we use Terzadaghi's classical bearing theory, right? This considers your shear. To consider settlement, we use the modified Shertman and Hartman method for some foundation settlements in cohesionless soil below structures, which is right here. Now, this figure here will better identify or better tell you how the system works. So the figure on the left is the load distribution without geosynthetics, while the figure on the right is the load distribution with the geogrid. So through this load distribution right here, you can see that geogrids can significantly improve the bearing capacity of the subsurface. Comparing that to the two figures, you'll notice actually that the distribution of the load here will result in either a higher load or higher factor of safety. So from 1:2 slope, the distribution would transfer or would become 1:1. So when you're considering, so there are also failure modes, right? When we do this technique or this method, we also consider different failure modes. So it's not all perfect. So this slide is to show you the major failure modes with respect to reinforced foundations using geogrids. So first, shallow failure above the uppermost reinforcement. This occurs when the fill material or the distance from the footing to the geogrid here is too high. So you would have a failure right here on the top. So the next type of failure will occur if the spacing between geogrids are too high, right? So from here to here, which would have a failure right here. Now, figure C will show foundation failure within the reinforced zone. Now, this involves more of a general failure and occurs when your foundation cannot sustain the loads. This one, D, is failure of distributed foundation. So what happens here is your foundation or the geogrids and the engineered fill is too thin and therefore would cause a failure right here. Another type of failure is reinforced foundation is wide, but then it's underlain by very weak soil and the thickness of your subgrade material is less or insufficient. That's why you'll have another failure. And the last one is occurs when punching of the reinforced zone. So this happens when your reinforced zone is too thin or it's not widespread throughout the entire foundation or footing. So just for you to be able to compute for GeoGrid raft foundation, the first is just to calculate the net allowable bearing capacity. So you have to consider, as mentioned before, you have to consider the criteria for shear and settlement. Then the next would be you would estimate this is more of a hit and miss. You estimate the thickness of the fill, and then you would then set a particular spacing of your geogrid raft. So you can do it at, let's say you estimate at 0.6 thickness, then you would add, you would say, you would place one geotextile layer or geogrid layer at 0.2 below the foundation, then another one after that at 0.2. So it's up to you because this is a hit and miss. Now, there's a note right here on number 4 that says that if you're dealing with an isolated foundation, since there are many, and it's not continuous, the best way for you to minimize the differential settlements would be to lay the geogrid on the entire footprint of the building. So just to give you a quick, so if the red is your geogrid, that is your foundation footprint, it would be best to install your, this is top view by the way, install your geogrid foundation like this. So with this, you can increase your bearing capacity in addition to reducing the number of settlements. By the way, this method does not this method does not address the problems with liquefaction, or directly address the problems with liquefaction. Okay, so this is a project we did in Salala. This is one of the largest loads, as you can see here, 450 kilopascal at the base of the concrete raft. This is the location of the project in Salala, Oman. This is the image of the tank. So as you can see, it's really large. And right here on this part, on the right side, let me just zoom to that. This is the blown up details of the configuration of the Paralink geogrids. So we had Paralink 200, 2 layers of Paralink 200, and 1 layer of Paralink 300. All of them are cross-laid. The thickness of the entire configuration is about was set as 1.5 meters thick, and the spacing per geogrid was set at 0.5, so 0.5, 0.5, and 0.5. And as you can see here, this is the offset we took that was set for this project. Okay. Now, with regards to the design, where is my cursor? There you go. We started at 450 kilopascal, and the estimated or the computed total settlement below the tank foundation was 1 millimeters. Now, due to the distributed load effect given by the geogrids, the pressure at this part here was reduced from 450 to 396, and even your settlement was reduced from 171 mm to 149 mm, which I think the settlement requirement for this project was 150. So, pasok. Just pictures of the installation of the geogrids. So from right to left there. First link of the Paralink, then this is the finished grade. So this is the ongoing construction and the final product. There you go. Another project we used this was in the Cebu-Cordova Link Expressway. So what we did here was we proposed a solution for the to stabilize the granular working platform. Now the bridge will have 2 layers. Oh, sorry. The product we used was the MacGrid EG. This is an HDPE grid. So Maccaferri supplied 23,000 square meters of the MacGrid EG40S and 16,000 square meters of the MacGrid EG30S. Now, having a safe endurable working platform that will the client wanted a safe and durable working platform that will support the heavy straddle carriers during the launching of the bridge girders in the causeway. So this is how we mitigated that. This was with Spanish contractor Acciona and Philippine firms First Balfour and DMCI. Okay. So what you can learn from this or from our past projects is there are a lot of you can definitely reduce the settlement, increase the bearing capacity, and you can confirm that using the plate load test or zone load test. And for this, it's usually advisable for only cohesionless soils, which undergoes elastic settlement because we're using the formula from Shertman. So our next topic would be basal reinforcement. Okay. Okay. So when you're dealing with embankments, there are a lot of things you can encounter, right? There are a lot of problems you can encounter. We have ground heaving and then separation of this. I forgot what's this called. So when you have low initial undrained shear strength, you have a high water table. It also addresses problems with stability and a lot more. So what the geosynthetics do is, or the alternative to these problems you see right here, is the basal reinforcement using geosynthetics. So by adding a layer of geosynthetics here, you would get there are a lot of benefits. First, you can have an increase in the design safety factor. So of course, you'll be more confident in your design. You'll also increase you can increase the height of your embankment. So you can add more load by adding more fill material. You can also, excuse me, you can also reduce the displacements during construction and a lot more. And because of this, because of the problems mitigated quickly by these rafts or by the basal reinforcement, you can decrease your construction time. So, basal reinforcement can be used on the weak foundation to improve the embankment stability. On top of piles, it can be used to distribute the load and optimize the pile design. And of course, over sinkhole to support embankment load. So if you have sinkholes here, you can just lay a pair of geogrids and you can address those problems real quick. So this is that same picture, but just for better visualization. Yeah, sorry. Okay, now, so this is the configuration of the embankment. So you have a drainage blanket right here, an anchor block, and this is where you lay your grids. So when you place a basal geogrid right here, you can increase the stability factor or the factor of safety with respect to the rotational stability of the embankment, sliding stability, overall stability, and even the foundation extrusion stability, as you can see in this next slide. Yeah, so by adding this layer of geogrid here, so the weight, you would reduce the susceptibility for foundation extrusion. You can decrease the susceptibility to lateral sliding, and because you actually improve it quite a bit, you would decrease the probability or the susceptible again to rotational failure, with including the global stability. And of course, because of this geosynthetic right here, you would have not less settlement, but the rate of settlement will be controlled. But take note, these factors are generalized. The factors that would govern the design would still depend on things like the geometry of the embankment, the stiffness of the reinforcement, then loading rate, soil type or soil stratigraphy, and characteristics basically of your embankment. But on a generalized view or to generalize everything, this is what you can get out of the basal reinforcement. So here we have strengths of up since 1977. Our basal reinforcement has strengths up to 1200 kilonewton per meter. It has high resistance to physical, chemical, and biological conditions. And also, its design life is 120 years. So these are the products Maccaferri currently has. So this is basal reinforcement for a project we did in Russia. Basically, we supplied 153,000 square meters of Paralink 700 GeoGrid. Another picture. All right. Okay. So now let's move on to the GeoGrid encased stone columns. So stone columns is used for both the cohesive and silty sand to increase the strength and decrease the compressibility. So this method involves inclusions of sand or stone to the geogrid and then encasing it with geogrids, as you can see right here. So first, removal of soil, then compaction of the stone and stone material. Then you would have the encasement of the geogrid here, and then removing of the filter, and then there you go, it's completed. The advantages of this method are quite a handful. So you would reduce the shallow foundation settlement, increase the bearing capacity and allow reduction in the footing size, mitigate the liquefaction potential. So unlike the other methods, for example, the geogrid foundation graft, it directly mitigates or directly has an effect to the stability or increases the stability, increases the stability of liquefaction against liquefaction, yeah. Then also provides slope stabilization, permits the construction on fills, and prevents earthquake-induced lateral spreading. So basically, what this slide sums up is that without the stone columns, so failure is imminent here, right? Because just by using stone columns, the most common failure is bulging failure, which usually occurs at 2 or 3 times the diameter of the stone column. So right here. Now, by using geogrids, you would have an additional confinement pressure or resistance to that bulging failure. And which is portrayed by the formula right here. So geogrid column reinforced composite can be estimated with this formula. So this Q ultimate C is the ultimate bearing capacity of the stone column, which can be estimated by multiplying the bearing capacity by 20. The AS is the area replacement ratio plus the ultimate bearing capacity of the soil, which if you need a quick estimate of that, Barksdale suggested a 5 times CU correlation, then multiplied by 1 minus the area replacement ratio. So our solutions is, again, reduce settlement, bearing capacity. You can also accelerate consolidation settlements. Now, geogrid encased stone columns are water permeable. So this can be used also as wick drains, function as wick drains. So it can also promote the consolidation. The GSC system cannot be completely settlement free. That's why we also compute for the total settlement. Right here, you have as illustrated or discussed previously, you would have an increased lateral confinement here on the 2D times or 3D area of Fajardo. So that's why it would be best to encase the geogrid up to this point, or better, the entire thing, which we will discuss further. Now, for the Murugesan and Raja Gopal of 2010, they created a formula or came up with a formula to get the ultimate bearing capacity of individual stone columns due to the possibility of bulging failure. So that's that right here. So this KP is so here now you would be considering the bearing capacity of the soil, the additional confining stress, which comes from the installation of the geogrid, and then you would also have the lateral soil stress, and you would be multiplying this with the passive earth pressure, coefficient of passive earth pressure. Typical parameters for the stone columns include the following. So yeah, I'll just give you a minute to. So column loads of less than 500 kN per column, settlement improvement factor of 1.5 to 6, ARR or area replacement ratio of 0.2 to 0.4, and then maximum depth would be 30, but 10 to 15 would be optimal. Okay, so the performance of geogrid encased stone columns, CU and D. Lee, they published an article where they focused on compressive load test. They performed compressive load test using steel reaction beams with a pair of anchors. They did that on two types of ground improvement measures. One was for the stone column, then the other one was for the RAM or the RAP, the rammed aggregate pier. Now for the load test, they used a 300-ton capacity hydraulic jack positioned on the concrete circular footing. And then I will now discuss quickly the results. So they did that on two sites, the Gimhae site and the Pohang site. So these two sites, okay, so here are the stratigraphy or the sections of the subsurface material. So you'd have here silty clay, and here you have clay sand. So that's the difference between the two. Now, what we have right here is the comparison of the rammed aggregate pier versus the geosynthetic encased stone columns. So as you can see, the GESC and the GSE 2D, the 2D and 4D means they encase the columns here. 3D, so from the top, 3 times the diameter, and then 4D, so 4 times the diameter right here. So you can see the results that you would have less settlement because of this, because the bulging failure was already addressed using the column, using the geogrid. So therefore you can increase the pressure, and that the performance of the geogrid encased stone columns is at par with the rammed aggregate pier, because one of the RAP is also susceptible to bulging failures. Now, for lateral deflection, as you can see here, this shows the performances of the GESC. So this is without the first here. The first is the first column shows without reinforcement. The second column will show a reinforcement or encasement length of 2D. So as you can see, for the Gimhae site where we have sandy clay sand, I think, you would have a bulging failure right here. under a load of 1,100. So if you increase that, if you increase the length of your encasement, you would then have a better or a reduced lateral displacement, as you can see here. Now for the pole hang site, yeah, you can directly see that under the current soil conditions, you would have very little lateral deflection compared to one without the encasement. So, for conclusion, the lateral bulging is considerably decreased due to the added confinement by the geogrid encasement. Then both the RAP and the GESC has a failure mode of bulging failure. Now, this failure mode here, again, as mentioned, is addressed by the confining effect provided by the geogrid encasement. Now, the recommendation in this article is at least 4D from the top, in case with geogrid to maximize the reinforced effect of the geogrid. Okay, so the critical, as you can see in the figures here, the critical encasement depth is 3D, or 3 times the diameter of the geogrid encasement. All right, so with that, I would like to say thank you. And if you have any questions, yeah, we're here. Feel free to chat. Thank you, everyone.
Thank you, Clem, for your very informative presentation. We will now go ahead and take some time for questions now. Just a reminder, please be sure to type your questions into the chat box, or you may click the raise hand icon and unmute. Okay, so we have the first question from Mr. Hakan. So, sa Lala project, why did you not use an anchorage block by wrapping around the end of Paralink, extending 2.5 meter out of the LNG tank foundation?
Okay, I think someone from our team would be better suited to answer this.
You may unmute for our technical team. You may now unmute your audio.
Hello, good afternoon, Hakan, or maybe good morning in Turkey. So basically, for the Salala project, I'd like to just comment. Um, well, normally we basically for any basal reinforcement, indeed, there's a very nice observation. We need to anchor the ends or termination of the reinforcement and satisfy the minimum wrap length. Um, and for this project, uh, we are actually not aware of the detailed design for the Salala, but in our case in the Philippines, we always wrap it to a minimum length as required by the standard. So um, for the Salala project, I think it would be better for the designer of the project to answer your question. But we'll take that note, Hakan, and we'll coordinate it with the Maccaferri subsidiary in charge for that project.
Thank you very much, Adrian and Clement, for the presentation. But I think generally, as you have said, the ends of the geogrid for any type of foundation reinforcement should be wrapped around, and it will affect the behavior enormously. I have already experienced this in various projects. Thank you again.
Yes, Akan, we do that also in the Philippines. We follow the wrap length requirement for the termination. Very nice observation on that. So we'll give you more answer on that when we contact the representative of Maccaferri in that project. Thank you.
Thank you very much.
Thank you, Sir Adrian. Thank you, Hakan. Another question from Mr. Brian Tan. When designing the geogrids for basal reinforcement of embankments, how do you calculate the pull-out resistance of the geogrid soil interface friction?
Um, Good afternoon, everyone. By the way, I'm Andrew from Maccaferri. Thank you, Brian, for that question. Actually, when we try to calculate not only the pull out but as well as the tensile strength required for the geogrid, we actually try to assume a failure mode of lateral spreading. So it's like the end of your embankment due to the pressure, the surcharge, and the weight of the embankment is actually pushing out the edge of the embankment. And what the geogrid does is provide support by preventing the lateral push made by the weight. So actually, Brian, we follow the code of BS, the British standard, and they gave some recommendations on the friction angle that we can use to take into account the frictional resistance of the mass or the frictional resistance exerted by the geogrids on the soil or on the mass of soil that is actually spreading laterally.
Thank you, Sir Andrew. I hope that answers the question. So we have another question from Mr. Selvaraha. What code of practice used for the design? Thank you.
Okay, if I may answer that question, the most popular code that we use in the design of the basal reinforcement is actually the British standard BS 8006. So they prescribe the checks that we need to do in designing our grids as basal reinforcement of the embankment. For in the case of geogrid encased stone columns, we are actually using the German code, the EBJO, where they recommend the design procedures in choosing the tensile strength or in calculating for the capacity of your column that is encased by geogrid. Okay. Of course, depending on the application for the geogrids used in pavements, you have the ASHTO and several other applications. And usually, we follow the codes that is more relevant on the application of the material or the application of the product. I hope I answer your question.
Thank you, Sir Andrew. So we have a follow-up question from Mr. Brian Tan. I see. Thanks for the reply. Are you able to conduct field or lab load tests, direct shear tests to confirm the developed skin friction?
Actually, Bri, in our grids and the products we usually have a technical note that we can provide the parameters that you can use. Usually, we don't do it per project, but in the grids we have, let's say in our Paralink and Paragrids, we have done the tests in our headquarters, and we can provide you the parameters that we can use on the pull out. However, I would concede that those parameters may not really reflect actual site conditions or conditions on the ground where you use the grids. So usually we have some general description of the soil, and then we can propose or we propose a a pull-out parameter that you can use in the design. Anyway, I'll try to get the materials and maybe forward you, Bri, for your information.
Thank you, Sir Andrew. Thank you, Mr. Brian Tan. So, are there any questions? Please, you may unmute your audio.
I just want to add for everyone in the use of these ground improvement techniques like the use of foundation raft and geogrid encased stone columns. To confirm the design, we would usually recommend to conduct a full-scale load test, which is actually the standard practice. If let's say we calculate a certain load capacity of our column, then before using in actual structures, we would recommend to conduct a plate load test and really confirm the capacity of that column. So that would somehow give a measure of confidence to the designer before using that techniques in any foundation scheme. Similarly, for the GeoGrid raft, we also recommend to conduct a plate load test to confirm the bearing capacity as well as the settlement behavior of the raft as calculated. We recommend that as part of the acceptance test for these methods. Okay, thank you.
Thank you, sir. Another question from Jackie. For government projects, are these products in the Blue Book?
I think we are, Jack, you're referring to DPWH projects. We know that DPWH or the Department of Public Works have been using basal reinforcement in several projects already. So among the method that we presented, I think the most relevant for the public works are the basal reinforcement. So I would say this method is acceptable to DPWH. I would know that there are already more than 5 projects. So based on my own personal knowledge with DPWH using a basal reinforcement. Thank you.
Thank you, sir. Are there any questions? Please type it on the chat box. Thank you. So again, I'll be sending an email for the survey and for the presentation link, for the presentation slides and the webinar recording to those who attended today. So make sure that you enter your complete name for proper identification. For those who did not, you may email, you may reply to my emails. Okay, I covered all of our questions. If you have further questions, you may email us and we'll make sure to assist your queries. So, great. Thank you, everyone. We appreciate you being here. Thank you, Clem, for the presentation. Thank you, technical team and the whole Maccaferri team. It was a pleasure being with you today. Thanks again for joining us today, and we hope that you will continue to join us for future webinar. Thank you and stay safe.
Thanks, everyone. Have a good day.
Thanks everyone. Happy weekend.
Thank you, everyone.